Hello students. In the last class we derived momentum integral equation. So what we are going to do today is to use that momentum integral equation to get an approximate expression for boundary layer thickness. Okay. So this approximation method, let us see one example of this approximation method for the case of flow over a flat plate. So this is the momentum integral equation in general. Okay, tau wall upon rho is equal to d by dx of u square theta, where u square is the velocity in the inviscid region, local velocity in the inviscid region, that is ue at x, and theta is momentum thickness at a particular location x, and tau wall is also at that particular location along the boundary layer, and then plus ue times dE by dx and times the displacement thickness at location x delta star. So we will use this equation for flow over a flat plate and see how can we get a approximation for delta. So first of all, for a flow over flat plate case, the free stream velocity does not change. ue is a constant because area changes are negligible. So ue is constant. So what will happen is, because of that, this term will become 0 because there is a gradient of ue. So if u is constant, this is 0. So this momentum integral equation simplifies to tau wall upon rho is equal to ue is a constant, so it will come out ue square times d theta by dx. That is the momentum integral equation for a flat plate case. Okay. So there were 3 steps. First, get an expression for u external. So for that we have done u is equal to constant, so u is known, and that will be simply equal to u infinity. Okay, next was assume a profile. Okay, so now what we'll do is we'll assume a velocity profile inside the boundary layer. So the simplest case is we assume a linearly varying velocity profile. So we assume a linear variation of velocity within the boundary layer. So what we say is the u by u infinity, which was f prime eta. Let's say this is a linear function, so that is a0 plus a1 eta. It's a linear function of eta. So within the boundary layer, the non-dimensional velocity profile is linear. That is our assumption. Now what are these two constants, a0, a1? Okay, how do you find that? Eta is simply y by delta that we had seen in the Blasius equation. Okay, so how do you find a0 and a1? Using boundary conditions. There are two boundary conditions because there are two unknowns, so we need two boundary conditions. First is the no slip boundary condition. So u at y is equal to 0 should be 0. So at y is equal to 0, eta also will be 0. So no slip boundary condition says u at y is equal to 0. That means u at eta is equal to 0 is 0, because at y is equal to 0, eta also will be 0. So u at eta is equal to 0 equal to 0. That is the one boundary condition. So if I put this, u by u infinity will be 0. So a0 plus a1 times eta is 0. So what you will get? Simply a0 is equal to 0. Okay, so first coefficient should be 0. Second boundary condition is that when you reach the end of the boundary layer, fluid velocity should become ue, which is equal to u infinity. So merger with the free stream, that u when you reach y is equal to delta should become u infinity, and when y becomes delta, eta becomes 1. So u at eta is equal to 1 should become u infinity. That means u by u infinity will become 1 at eta is equal to 1. So a0 was also already 0, so a1 times 1 equal to 1, so a will become 1. So that way we can find both the coefficients and then we'll know the linear velocity profile. Okay, so the linear velocity profile will be simply u by u infinity is equal to eta. F prime eta is equal to simply eta. Okay, now this is known. Now in boundary in the momentum integral equation we need tau 1 and we need theta. So first let us find theta, which is momentum thickness. Momentum thickness expression for theta is this: integral of u by u infinity times 1 minus u by u infinity from 0 to delta. So I can this is in terms of y. I can convert this integral in terms of eta. So eta is y by delta. So d eta is 1 upon delta times dy. So dy I can write as d delta times d eta. Okay, and then at y equal to 0, eta is 0, and at y is equal to delta, eta is 1. So momentum thickness will be this: integral of delta times integral of u by u infinity times 1 minus u by u infinity from 0 to 1, where u by u infinity will be now a function of eta, and this is known. So we can just put u by u infinity using linear velocity profile. So theta is equal to integral of u by u infinity is eta times 1 minus eta within 0 to 1. So this is eta, integral will be half eta square minus eta square, so that is eta cube by 3. So when you integrate, finally you get theta is equal to delta by 6. This is delta. This will be by 6. So we have momentum thickness. Momentum thickness is simply delta by 6. Okay. We have momentum thickness. Then we need wall shear stress. So tau wall is simply mu del u by del y at y is equal to 0 at the shear stress at the wall. So this also I can write del u by del y can be written as del u by del eta times del eta by del y, and del eta by del y is 1 upon delta. So this will become mu upon delta, and then del u by del eta is y is equal to 0 means eta is equal to 0. So that is the expression for wall shear stress. Okay. Then u is u infinity into eta. So del u by del eta will be u infinity into just u infinity. So tau wall will come out to be mu by delta times u infinity. This is the wall shear stress. So now everything is known. We can put everything back into the momentum integral equation. So that was tau wall upon rho is equal to ue square d theta by dx. Tau wall is this 1 upon rho mu by delta u infinity, and u is simply u infinity. So u infinity square, and then d by dx of theta, where theta was 1 by 6 delta. So 1 by 6 d delta by dx. Okay. Now you see that this is a ODE in delta with respect to x. When we solve this ODE, we'll get delta as a function of x. So we can integrate this ODE. There is one delta here, so we'll take it with the delta and everything on the other side. Okay. So eventually when you integrate, you'll get delta by x is equal to square root of 12 upon rex. So rex is what? This u infinity x by nu. Okay, u infinity x upon nu, that is rex. So finally we have an approximation for boundary layer thickness. Delta by x equal to 3.46 upon rex, and the actual work 4.9 upon Rex in Lassier solution. So you see that linear velocity profile is under predicting boundary layer thickness. So if you compare this with the Lassier solution was more complicated, and it involved solving it involves numerical integration also. It was not possible to solve it analytically. But now here we have an analytical method, which is also not very complicated, right? All the things what we did, the algebra is very trivial. So here we have this momentum integral equation, which can be integrated very easily compared to Lassier solution, and we can get a approximation for the boundary layer thickness. And then what you can do is, how is it useful? From experiments we already know the boundary layer thickness approximation, like what is the thickness as a function of x. Then whatever velocity profile gives us the best approximation, that is like reverse engineering. We first get the approximation of delta, compare it with the experiments, and then we can say that the velocity profile that we have assumed is very close approximation of the actual velocity profile within the boundary layer. Okay, that is how this momentum integral equation can be used to obtain delta. Okay, now this was the example where we used linear velocity profile. We could improve this. We could assume second assumption. The second improvement could be what? We could go and assume a quadratic velocity profile instead of linear. Okay, so we could also assume a quadratic velocity profile and then also solve this equation similarly and get a hopefully better approximation for delta. Okay, so now what I wanted you to do is stop here. Okay, stop here, take a notebook and try to do it yourself. Try to assume a quadratic velocity profile, apply boundary conditions to get the unknown, and then repeat the process which we did and get an approximation for delta. And when you are done, come back to lecture. I will show that solution in the next slides. Okay, so hopefully you have attempted. Now let us see whether your attempts are correct or not. Okay, so next we will assume a quadratic velocity profile. U by u infinity is equal to a naught plus a1 eta plus a2 eta square. Again, these coefficients we can get from boundary conditions. So already two coefficients we determined using two boundary conditions, no slip and merger with the free stream. We need another boundary condition to get this coefficient a2. Okay, so first boundary condition, no slip boundary condition, we give a naught is equal to 0. Then merger with the free stream says that u by u infinity is 1 at eta is equal to 1. So that will give us an equation that a1 plus a2 is equal to 1. Right? You put eta is equal to 1 here. That should be equal to u by u infinity, which is 1 at y is equal to delta. Then third boundary condition will come that when we reach the end of the boundary layer or the edge of the boundary layer region, we reach the region of inviscid flow where shear stresses should become 0. So when we apply this no shear boundary condition at the edge of the boundary layer, so what is that? That mu times del u by del y and y is equal to delta should be 0. So that will give us del u by del y should be 0 at y is equal to delta because mu is not 0. So you can convert that into eta. So del u by del eta also should be 0 at eta is equal to 1. Y is equal to delta, then eta is equal to 1. So at eta is equal to 1, gradient of velocity u with respect to eta should be 0. You do that, you'll get a1 plus 2a2 eta, right? When you take gradient of this, what you will get? a1 plus 2a2 into eta, and that should be equal to 0 at eta is equal to 1. So you'll get a1 plus 2a2 is equal to 0. So there are two equations, two unknown, that can be solved. When you solve, you'll get a1 is equal to 2 and a2 is equal to minus 1. So this is 0 and a1 is 2, a2 is minus 1. So eventually the quadratic profile will be twice eta minus eta square. U by u infinity is equal to twice eta minus eta square. That is the quadratic boundary layer profile satisfying boundary conditions. Again, then using that profile we can find out momentum thickness. So we put u by u infinity as this, and then we need to just do integration of this. So this is just a polynomial. It can be analytical. This can be integrated analytically. Finally, after you do the integration, you should get theta is equal to 2 by 15 delta. Okay. So initially in the linear approximation, what we get was 1 by 6, and here we are getting 2 by 15. Okay. So which is smaller? I think this is smaller, right? Because yeah, this is smaller. So this momentum thickness is smaller than the linear case. Okay. Okay, so we have this. Then next is tau wall shear stress. So wall shear stress was this mu by delta, del u by del eta is equal to 0. So when you differentiate this, you'll get 2 minus 2 is eta, and when you take eta is equal to 0, you will have only 2 left. So this will become 2 times mu by delta into u infinity. Okay, so this is the wall shear stress. Both are known, wall shear stress and momentum thickness. You put back into the momentum integral equation, you will get delta. The momentum thickness, momentum integral equation, tau wall upon rho is equal to u square deta by dx. Tau wall is this 2 mu by delta u infinity, and theta was 2 by 15 delta. So we get this. Okay, so only difference what you'll get is the coefficients will be different. Rest of the things are same as compared to linear case. So coefficient will be different. So eventually when you take this time, you will get delta by x is equal to square root of 30. I think in linear case it was square root of 12. Okay, so delta by x will be approximately 5.48 rex divided by rex. So again, this is also away from the exact solution. This is actually over predicting, but you can see that you can calculate the percentage error. So I think you will find that, hopefully you will find that the percentage error in this case is smaller than the percentage error in linear case. So this way you can keep on continue, you can assume different profiles and then get an idea of this boundary layer thickness and accordingly the velocity profile. Okay, so that's all about the momentum integral equation. So I hope you realize that this is much easier to do as compared to that Blasi solution. So that is the important of this Karman momentum integral equation where we are seeing this. Okay, now we see a application of this boundary layer concept. Okay, so we look at the entrance, we try to find out the entrance or development length in a channel or pipe flow. So for example, this is a channel, parallel plate channel, where distance between the plates is 2h. Okay, so till now what we have seen, the whatever we do analytically, what we were assuming that the flow had become fully developed. These plates were very long, so the flow between the plates was fully developed. It was not changing with x, where x is the length along the plates. Okay, and what we found was that the velocity profile between the plate is parabolic, right? So now what we are going to look at is what happens at the entrance of this channel, because fluid somehow will be pumped in within this channel, right? So what happens at the entrance? So what will happen is, let's say there is a free stream flowing, right? And there is some free stream which is flowing with u infinity, and then you put this channel in that stream. So for example, there is a river flowing and you just take this channel in the river. So what will happen is, as soon as this free stream enters the channel, it will interact with the wall, and then what will happen at the walls, boundary layer will start forming. Okay, so whenever a free stream will interact with some solid surface due to no slip boundary condition, what will happen, this boundary layer will start, boundary layer will form on the surface, and as we go along the surface, the boundary layer thickness is going to increase. Okay, so boundary layer will develop at both the walls due to no slip boundary condition, and as we go move along the channel, it will grow in size. However, in this region, the fluid will not feel any effect of wall. Why? Because boundary layer, all the effects are restricted to boundary layer region. Whatever viscous effects are there, that are present here only. So there will be no viscous effects felt by the free stream in this region. There will be other kind of effects because area is changing, but no viscous effects. Okay, so central region will remain inviscid, right, in the starting of the entrance. Afterwards, it has become everywhere flow is going to become, there are going to be viscous effects everywhere, but at the entrance, for some length, there will be no viscous effects in the central region. The viscous effects will be restricted to only near wall regions, and that region, near wall region, will keep on growing. So what will happen is, at the entrance, boundary layer thickness is almost zero, and as you go along, boundary layer thickness increases. So the area available for the inviscid region, that will keep on decreasing as you move along. So from inviscid flow point of view, as area is decreasing, what will happen? That inviscid core will accelerate. A1v1 is equal to A2v2. So central core will accelerate. Okay, and eventually what will happen is, you will reach a point where both of these boundary layer, they will merge, and once they both the boundary layer merge, there is no inviscid flow region is left. Okay, so boundary layer from here will merge with boundary layer from here, and then what will happen, further downstream, those boundary layers will interact. So immediately here flow will now become parabolic, because within the boundary layer we don't know whether velocity profile is parabolic. From whatever we have derived till now, it was very complicated. It was not a just simple function. We had a series formula for boundary layer profile. So what will happen is, once these boundary layer merge together, there will be more changes in the velocity profile. So those velocity profile will further change along the plate length, and then after a length, you will reach that fully developed condition where velocity profile will become parabolic and it will stop changing along x. Okay, so once this boundary layer thickness merges, after that only flow will become fully developed, but there will be some distance further along. Okay, remember that. Okay, so what we want to do is to find this development length, this length of the channel that is required for flow to become fully developed. That is called development length or entrance length, that we want to find out. So what can we do to find this out? We don't know what will happen after merger. That is a complicated situation. We have not studied that till so far. But what we have done is, we have studied this boundary layer. So what we'll do is, we'll try to approximate development length as the length till this boundary layer merges. Both the boundary layer merges. We'll say that the development length is approximately equal to this length, to the point, from the entrance to the point where both the boundary layer merges. The actual length will be little bit higher than that. Okay, so first let us try to find this distance, LE. Okay, so how can we find this out, Ellie? So till now what we have studied is only, or what we know, the solution. We have studied boundary layer in general for flow over bodies with small curvature. But as far as solution is concerned, we only know solution for flow over a flat plate, right? So what we can do is, we can assume that okay, the boundary layer growth in this channel, let us approximate that with the boundary layer growth for flow over a flat plate case. Okay, let us assume that. However, this is not true. Why? Because here free stream velocity is going to change significantly. There is a very small area available for the free stream, so there will be significant acceleration of free stream. So definitely the boundary layer growth will be very different from flat plate case. But since we already only know this, let us try to assume this. If we actually go on try to solve for boundary layer profile in this region, that will become very complicated, because the change in this free stream velocity will depend on the boundary layer thickness, and the boundary layer thickness will depend on the free stream velocity. That is a very coupled kind of problem, difficult to solve. Okay, so first like to try to get a very simple approximation based on what we know. So assuming that the boundary layer thickness approximation is for a flat plate case, delta by x is equal to 4.9 upon Rex. That is the flat plate boundary layer growth approximation that we are going to use here. Okay, now what we say is that when x becomes development length, the boundary layer thickness should become h. So boundary layer will form on both of the plates and it will go symmetrically, right? There is no reason for one boundary layer thickness to become larger than other. Everything is symmetric around the center line. So both boundary layer will increase in thickness symmetrically, and they will reach h and h, and they will merge. So boundary layer thickness will become h, delta will become h, and x is equal to Le, where 2h is the channel height. Okay, so I can use this equation. Delta is h, x is Le, and 4.9 upon Re, x is Re. Okay, what is Re? So for a flat plate case, Rex was u infinity x by nu, right? So what we'll say, instead of u infinity, what we are going to use is 4.9 ue Le by nu, where u is velocity here, the velocity in the inviscid region, ue at x is equal to Le. Okay, so what we are saying is locally anywhere the boundary layer thickness is being approximated by the flow over a flat plate case. So locally, when we are approximating, we'll use local free stream velocity, ue. Okay, what is ue? That we need to find out. ue is what? The central inviscid region velocity. So that will be related to u infinity somehow, because this region is going to accelerate. Okay, so we do a little bit algebra here. What we do is, we divide and multiply by u infinity into 2h. We multiply and divide. Okay, so u infinity into 2h divided by mu, that is Re. When we multiply and divide, eventually after algebra you will get this. H by Le is equal to 2 into 4.9 square upon Re times u infinity by u, where Re is Reynolds number based on channel height. Okay, so this Reynolds number was based on x or based on Le, but for when we are studying flow in a pipe or flow in a channel, we need to talk in terms of Reynolds number based on channel height or channel or pipe diameter. So that is why I just converted this Rel to Re. Okay, How can we relate U infinity and UE? So for that we can use the concept of displacement thickness. So at the inlet, what is the mass flux? U infinity into TH 2H. Okay, and from mass conservation, same mass flux should exit from here. Whatever mass flux is entering here should leave from this cross section because these are walls. What is the mass flux leaving here? So for that we use the concept of displacement thickness, right? So here velocity profile will be somewhat different, right? It will not be constant, so we'll have to use integration to find flux through this cross section, but we can avoid that by using concept of displacement thickness, which define that displacement thickness is you have this boundary layer. We can remove this boundary layer profile, and what we can say is we shift this plate by the distance of delta star and then use constant flow approximation or the inviscid flow approximation. Okay, so this plate will be shifted by delta star and this plate also needs to be shifted by delta star, and then in that region we can say inviscid flow velocity that will give us the flow rate. That flow rate will be same as flow rate what you get from integrating within the boundary layer, right? So here velocity is ue in the inviscid core, and what is the height left? So initial total height is 2h, and then you are displacing this plate delta star in this distance and this plate delta star in here, so minus 2 delta star. So ue times 2h minus 2 delta star, that is the mass flux leaving through this cross section. Okay, and then for flat plate case we already know the relation between delta and delta star. So delta star is approximately 0.35 delta, and what is delta here? Delta is h, so delta star is approximately 0.35 h at this point, so we can keep it here delta star. So when you put delta star here, ue will come out to be 1.54 u infinity. Okay, that is the inviscid core region velocity ue. Okay, you can say center line velocity. So after that, that is the center line velocity, right? Because here you have the inviscid core approaching a line, right? This area is going to become a point light. Okay, and if you recall, in the case of fully developed flow in a channel, I think if I remember correctly, the center line velocity was 1.5 times mean velocity. Okay, so this center line velocity, you see it is coming 1.54. This is more than 1.5. So what will happen afterwards? It will slow down a little, by a very small amount, and then it will become fully developed. Okay, so coming back to what we were driving, so we have found that ue and u infinity are related by this. So we can use that and put back into our formula for development length. So that was h by le. I have just reversed that. Le by h is equal to ue by u infinity and then 1 upon 2 4.9 square re. ue by u infinity is this 1.54. So finally le by h will come out to be 1.54 by 2 4.9 square re, and this we can calculate. So le by h will come out to be approximately 0.03 re. So see, using this information for the boundary layer or knowledge of boundary layer can enable us to gain approximation for development length, and it is approximately 0.03 re. This is for a flat plate case. Similar thing, I will leave it up to you. Similar thing you can do for a pipe. So instead of a instead of having a channel, you will have a pipe of diameter d, and you could there also you assume that linear variation, sorry, flat plate, you assume flat plate boundary layer, and then after doing that you will find that for laminar pipe flow, Le by d will be approximated by 0.06 Red, where Red is Reynolds number based on pipe diameter. Okay, so this also is valid for laminar flow only, because whatever boundary layer approximation we were using, flat plate boundary layer approximation, that are derived for laminar flow. We have not derived anything for turbulent flow. Whatever we have done is for laminar boundary layers. So these approximations are for laminar flow in pipe or channel. Okay, and just for your information, the value of RED for laminar for flow to become turbulent, so laminar to turbulent transition. So in this pipe flow, as you keep on increasing flow velocity, after the flow certain flow velocity, flow will become turbulent. So the RE, Reynolds number for laminar to turbulent transition, is close to 2300. Okay, so if Reynolds number is less than 2300, we can estimate the entrance length using this expression. Okay. Okay, so hopefully everything is clear. So we'll stop by here now. We'll continue in the next class.